Okay, we're solving some questions here about a real battery, or sorry, an ideal and then a real battery. So if we're assuming the battery is ideal, then we're going to say that this internal resistance doesn't exist and we want to solve the circuit. So I'll make a chart here. So resistance, current, voltage change. So we have a 180 ohm resistor, a 220 ohm resistor, 330 ohm resistor, and then we want to figure out the total. If we figure out the equivalent resistance, I can break those two are in a simple series, so that's 400 ohms, and then if I combine that 400 ohm branch with the 330 ohm branch, those are in parallel, so we have to do the 1 over action. This will give us 180.8 ohms total. So plus 3 volts across the battery. Once I've gone across the whole thing, I'm going to have to lose all 3 volts. So then I apply Ohm's law there. I is 3 volts over 180.8 ohms. This will give us 16.6 milliamps of current. So that's the current through the battery. It's going to get here to this branch and some will split that way. This is our 16.6 milliamps. Some will split and go this way and some will split and go that way. So neither of those will be the current through, and none of these resistors will have that amount of current through them. But if I use the loop rule, plus 3 volts here, and I go around the outside, minus 3 volts, now I'm back. So this 330 ohm resistor, I have to lose 3 volts across that. I have to lose 3 volts across the 180 and the 220 ohm resistor together, but I don't know how much over either. But since I have 2 of the 3 here, I can say that I is 3 volts over 330 ohms, which will give me 9.1 milliamps. Alright, so that's down this branch, 9.1 milliamps. Now I can use the junction rule. 16.6 milliamps flow into the branch, or into the junction. 9.1 milliamps go down this one, so 7.5 milliamps go down that one, so that I have the same total current. Because these are in series, they both get the 7.5 milliamps. And now I can go down this way using Ohm's law, and voltage change across each of these is just I times R, so it's different across the two. Minus 1.35 volts, minus 1.65 volts, but together that would be minus 3 volts, which is what I expected from the loop rule. So all this checks out from the perspective of the junction rule and the loop rule. Okay, now I'm saying that instead of being an ideal battery, we have a real battery and the terminal voltage is 2.9 volts, which means that the voltage change across this little resistor is 1/10 of a volt. I'm going to use the loop rule here. So if this terminal voltage is 2.9 volts, then when I go across that 330 ohm resistor, it has to be 2.9 volts as well. All right, I'll go over here to the side, make a new chart, start to put some of these things in. So there's the internal resistance, which I don't know. There's 180 ohm, the 220 ohm, the 330 ohm, and then the total, which I'm not sure of as well. I do know that I'm going to lose 3 volts across the whole thing. If this terminal voltage is 2.9 volts, I know that I lost 1/10 of a volt across the internal resistor. I know by the loop rule, as I just said, that I lose 2.9 volts across the 330 ohm resistor, negative 2.9 volts. Alright, that's enough to get me this current though. So that's 2.9 volts over 330 ohms, which will give me 8.8 milliamps. That's just across this part. But across these two together, right, those two together are 400 ohms. I know I also have to lose negative 2.9 volts. I don't know how much I lose across each one, but the total will be 2.9 volts because I'm 2.9 volts across the whole battery, so it must be minus 2.9 volts across this branch. I don't really care how much is in either, but this will let me calculate that total. This is 2.9 volts over 400 ohms. And that will give me 7.3 milliamps. Okay, so if I look at the total current, right now in this new case I'm 7.3 milliamps on this branch, a little bit less, and 8.8 milliamps on this branch, also a little bit less. But the total now going through the thing has to be the sum of those, so 16.1 milliamps. So that's the total that is through the battery, which is also through the internal resistance. So now I can apply Ohm's law to that resistor. So 0.1 volts is 16.1 milliamps times R. So R is 0.1 volts over 16.1 milliamps, which is about 6.3 ohms. So that is the internal resistance, which is what we were looking for. We also want to know the power dissipated by the set of resistors, not including the internal resistance, and then by the internal resistance. So not including the internal resistance, so that's my 3 resistors here. Power is I delta V. I know we figured out that the total current in this case was 16.1 milliamps, so that's through all the resistor, through the whole resistor network. The voltage change across the resistors is 2.9 volts, which will give me 46.4 milliwatts. And for the internal resistor, so this is not R, and this one is for R. Again, I delta V, the current that flows through the internal resistor is 16.1 milliamps because it's in the battery, so it gets the total current. The voltage across it, though, is only 0.1 volts, so we get 1.6 milliwatts. So if we look at where our energy is going, most of it is going into the device, into all the resistors, rather than into the internal resistance of the battery, which, of course, is what we want.